Okay, let's start with Dromajo. The best way to explain Dromajo, in my opinion, is by explaining the technique it implements. And the technique it implements is a concept of co-simulation. And that is on-the-fly comparison with the golden model. I mean, at this point you might ask, what is a golden model? It is nothing but very high-level software abstraction of the processor. It's basically an emulator. It's in independent software. It's usually being developed in a different team, completely separate from the RTL designers. It's very simple, has no implementation details, it has no timing details. So things like cache misses, TLB misses, branch mispredictions, all those things being ignored by the golden model. And the changes to the architectural state happen basically on the instruction level granularity. Now, this couple of slides are animated slides. It's going to help us understand the communication that happened between two independent softwares, right? So on one side, we have a test bench with the processor under test being instantiated as an object and its memory. So we compile that software into some executable. And on the other side, we have the golden model, our emulator, right? So after those two executables, so after we have those two executables ready, we start the execution. And the y-axis, if you will, is the time. So we start the execution. At some point, we need to load the binaries that we're going to run. At that point, we need to synchronize the memories and the architectural state of the test bench and the golden model. And we have this communication channel that basically signals the golden model to get the data and synchronize the architectural state. We continue execution. At some point, we commit one instruction. We commit our first instruction. That's when we signal the golden model and tell golden model to commit instruction on its own side and perform the comparison. So green box basically indicates that with the comparison of the committed values are actually matching on both sides. And that's the success. We continue the execution. At some point, there might be the cases when the committed instruction have different values, and that's when this whole system, this kind of technique basically tells us that something wrong is going on here, because architectural state has to be all the time, this architectural state of both sides has to be the same always, no matter what. At this point, we halt the simulation and we start investigation, we start debugging. Now, Dromajo is exactly what I've just explained. It is the state-of-the-art co-simulation verification infrastructure for 64-bit RISC-V processors. It implements RV64 GC model, and it designed specifically for co-simulation purposes. It is fast, it is lightweight. Now, very important bullet point right here. Dromajo is an open source. Dromajo is an open source software. It is hosted in the Chip Alliance GitHub repo. So if you were to design a RISC-V processor by any chance, go check it out. Make sure you integrate Dromajo into your processors. It's going to find a lot of bugs, I promise. Yeah, let's go into some more details of Dromajo. So the way we integrate Dromajo into our test bench infrastructure is by linking Dromajo as a shared library into the test bench, into the simulator. So RTL implementation right here, the box in the middle, communicates to Dromajo through DPI calls. So that communication channel that I explained in the animation are actual DPI calls in our case. And it is super simple to integrate, right? So it's just a matter of implementing 3 APIs, just calling three APIs of Dromajo that will basically implement this communication between the model and the RTL implementation. Now the first one is the loading, is the synchronization of the memories, right? So when we load the binaries, we call Dromajo init, which initializes the memory of Dromajo by synchronizing it with the RTL. Another one, when we commit, we call Dromajo step API, which tells Dromajo to commit one instruction and perform the comparison. If comparison is successful, we continue. And there is also this Dromajo raise interrupt API, which I want to emphasize because not many tools actually support this. Even some commercial tools don't support that. So what it allows to do is supporting the asynchronous interrupts, right? So it can happen anytime, and we don't know when it's going to happen. And the problem, if you don't support that, the RTL implementation and the Dromajo and the golden model will start to diverge, right? Because the RTL will start executing the interrupt routine, but if the golden model doesn't support that, the execution flow will start to diverge. And Dromajo, basically, fortunately, it supports that, which means we can co-simulate even inside of the interrupt routines. And in the case when the mismatch happens, Dromajo holds the whole simulation and dumps specific information to the engineer so that he can start debugging. Now, Dromajo also addresses the issue of productivity with the checkpoints. I mean, this checkpoint is very novel, I think, in the verification space. So previously, we have seen this picture on the left, right? So that's when we load the actual binaries into the Dromajo instance and the memory. We can also implement Dromajo as depicted on the picture on the right. So we can run Dromajo standalone, meaning we can load some random instruction generated tests. We can boot Linux. We can put unit tests inside of Dromajo and let it run for many cycles, and then dump the checkpoint. And the checkpoint is nothing but the snapshot of the architectural state, which we can then load into our simulator and start from that point. So I mean, the nice use case is basically boot Linux in Dromajo, run it for billions of cycles, and take the snapshot of the architectural state after billions of cycles, and start the co-simulation from that point, instead of waiting for billions of instructions when we were to load the binaries. Yeah, and what is the checkpoint? Checkpoint is nothing but a generated bootron that brings any number of processors into the same architectural state. So it's basically a code that you execute, and after the execution of that code, on the same course, it's going to bring the many cores into the same architectural state. And obviously, we'll also have to dump the memory so that the loads and stores are not going to fail the co-simulation. So, nice use case of the checkpoints that address the productivity is that we can boot Linux with Dromajo and let it run and basically dump many checkpoints at different points, right? So this might be 1 million instructions, this might be 500 million instructions, and this might be like 2 billion of instructions being executed in Linux. And then we can spawn all those checkpoints across many cores and execute the co-simulation in parallel. So this is a really nice feature. This really saves a lot of times of the design verification engineers, as we can execute many co-simulations in parallel.